So good afternoon, and so today in tutorial 5 we'll be discussing problem set 5, and at some level I would say that most of this content is will be discussed usually in much more detail, in a second course in statistical physics, or if you do a condensed matter physics, depends on your teacher. That teacher might do this. Okay, but we are pretty close to understanding at least some few ideas, and so this is supposed meant to be a first introduction to what I call critical exponents and the scaling hypothesis. Okay, so there are two problems, and okay, so just so we'll work out some things and we'll check some things, but don't expect to have like 100% understanding. Anyway, in any event, all my lectures, if you can understand 25% right away, you're doing pretty good. So the first problem is basically to define uh, for uh, exponents which are called alpha, beta, gamma, and delta. There are a few more, but okay. And so what we can do is we have an approximate solution. So we can compute alpha, beta, gamma, and delta uh, for our mean field solution. And so we will do the computation, and we will see that we'll get 0. Half I think we've already done. 0 also we probably have done in class. Okay, gamma and delta we haven't, I think. So gamma turns out to be 1 and 3, and the 2D Ising model has an exact solution, and so alpha there is also 0, and then beta is 1/8, gamma is 7/4, and delta is 15. Okay, and for the 3D Ising model it is 0.1. So this is exact solution from an exact solution. Second line, first one is we will be doing these numbers. Third one is Monte Carlo, or there's something a new method called conformal bootstrap, also which lets people achieve higher precision than Monte Carlo today. And so the numbers are only approximate to some accuracy, but that's good enough. 0.1, 0.33, 1.24, 4.77, etc. Okay, so first thing to notice here is that so there is a dimensionality dependence on alpha, beta, gamma, and delta. Okay, but when we did our mean field solution, actually I didn't mention 1D Ising model. We will do the exact solution in the lecture tomorrow, and so there will be no phase transition really. That will happen at t equal to 0. That's not a phase transition. Okay, so the critical temperature is 0. So okay, so but the mean field says something totally bland for all of them. Turns out that for 4 and above, the mean field answer is exact. Okay, so roughly the logic is that as we go to higher and higher dimensions, the coordination numbers increase. I mean, this is not the precise thing. So there will be, in some sense, the mean field gets better, and so and fluctuations become less important. By fluctuations, I mean fluctuations about the mean. So we did not. So we assumed that the average value of sigma was m, and that's about it. We never worried about how it deviated from the deviations from that value of m that we got from the. This thing is called fluctuation, and so fluctuations are important in say 2 dimensions, etc. Okay, so mean field is good for some fairly high dimensions. So there is some critical dimension. I think it's for this. It's 4. Okay, so but you can see that the mean field answers are not quite don't work in 2D and 3D. Okay, so and I'm drawing this table here because this is a table worth keeping. Okay, and because we can compare with some other. We'll be doing some other problems where we will look at we look at these exponents again, and they will appear again. Okay, so that's target of this problem 1, which is to bring together certain ideas. And so near a second order phase transition again, you can so we have seen that we can define critical exponents which track how the singular behavior as you approach the critical temperature. Okay, so away from phase transitions, usually the correlation length dies exponentially fast. So I have to define what I mean by correlation length. So suppose we have, I'll define it in the spin model, but it could be for any two observables, sigma at I and sigma at j, and you want to work out its correlation function. And so let's say we are at t greater than tc. If you can do this computation, by the way, and we haven't done it, so we'll find that it goes like it falls off exponentially. So Raj is the separation between I and j, and xi is some length. That length is called the correlation length. Okay, so Raj is the distance between the points I and j, and xi is called the correlation. However, as we approach the critical point, this correlation length diverges. That means it goes to infinity. So if the denominator is going to infinity, this term will kind of is going to infinity. So this will just become a constant. It will be independent of this thing. So, but what you will see is that when you approach a critical point, this happens. But then, and this is the way it will approach infinity, if you wish. And then we'll also find that this behavior becomes replaced by something else, like this. It's still Raj, and it is defined as d minus 2 minus eta. So there are two more critical exponents which we will not determine. Okay, so in the second part we will discuss this idea of scaling
Sir, what
hypothesis.
is new value of new?
We haven't computed that. And, okay, so nu and eta I have not given the numbers also. Okay, so yeah, they are known. I mean, if you're asking me what is it for 2D Ising model, etc., it's known. Okay, and eta.
Okay.
So we'll get to this. Okay, but I thought I will do something called hyperscaling, which will involve nu and eta, and I did stop short because that will make it even more technical. So I didn't do that. Okay. So that was the idea when I started writing this, but I thought you should know these terms. Okay, so let's get on to solving the problem sheet, and so let's do that. And this is where my problem is now. Okay, doesn't matter. So I'll keep going back and forth, and the recording will get mixed up. It's not a big deal, but let's just do that. Okay. So so this is the theme, and one second. So I need to change. Okay, so can you see my tablet now?
Yes.
Okay, very good. So so problem one is about defining critical exponents. Okay, and computing them in the mean field theory approach. Okay, so just give me a second. I don't want to keep going back and forth, so I'll bring my notebook. I just need a second, 1 minute to bring it. Okay. So the first one is through C, and the definition is it goes like T minus Tc power minus alpha. Okay. And just I want to make a remark here. It can happen that critical exponents are different when you approach from, say, T approaches Tc minus, that means from below, and when T approaches Tc plus. Okay, so some books will define, so in principle there are two exponents which we can call alpha plus, alpha minus. Okay, but if they happen to be equal, we just say alpha. Okay, is this clear that this is the definition? Okay, so let's do the computation now. So we need to, so what is C? Okay, and what is U? We need to compute U. So U is nothing but expectation value of H. Okay, and let's say we want this at B equal to 0, and H with B equal to 0 is just minus J expectation value summation Ij sigma I sigma J. I think we did this in class, it doesn't matter. Nearest neighbors. Okay, in the mean field thing, the product, this will be equal to, this is now, until this point it's exact, but now we'll make some this thing. So first thing is that, let me just write this. So, okay, so this is equal to m in our definition, and this is also m, so it becomes m squared. So you get minus j n number of sites, and then y is half the coordination number. Okay, times m squared. So this is what we get as u. Okay. Does anybody remember what was TC?
It is JY divided by 4 KB.
Okay. So TC is JY divided by 4K. Thank you. Okay. So, okay. So what is it we want to compute? We want to compute du by dt now. Okay. And this will be equal to minus, let's leave all these things, a and y times 2m dm by dt. Okay, so actually we had worked this out in class, didn't we? Okay, so first thing is that for t greater than tc, m is 0, dm by dt is also 0, so c equal to 0. But for t less than tc, okay, you have to do some work, and so what we see, m of t goes like 1 minus t by tc power half. Okay, this is I showed this in class. And this happens to be another exponent. Does anybody remember what this is called?
Beta.
Okay, thank you. Okay, so but now we have to do dm by dt of this. Okay, and so if you do dm by dt of this, you will get, it will become 1 minus t by tc power half, which will become minus half. Okay, so dm by dt is proportional to, because we are only interested in the singularity part of the story, you get a minus half times some constants. So that's why I'm not using equal to, I'm using that tilde sign. Okay, so but m dm by dt. So this goes like plus half minus half goes to a constant, and the constant we worked out, which was just 3 by 2 nk.
So what do you mean by singularity here?
At t equal to tc, it's infinity. dm by dt
What
blows up.
is
dm by dt blows up. It's 1 by
okay?
1 by a 0, no? Inverse 1 by square root of
Okay.
0. Okay. M is non-singular. It goes to 0 as this thing, and not it goes to 0. Okay, but still there was a cusp, if you remember, if you draw the plot. Okay, so what we get is C. We have a formula, but it tends to constant, and you can work out. I mean, we know it in the neighborhood. Okay, so now both of them. So what is the power? So so you can see that now. Go back to this definition of alpha, which is here. So it goes as constant when it's close to 0. That's only possible if alpha is 0. Okay, is this clear? The logic. That's so. This implies that alpha plus equal to alpha minus equal to 0. Okay, so we just write alpha. Part B was m of t. How does it go? As power beta. And I'm not going to show the computation, so because we did this properly in class. So okay, is this fine? So in this case, really it is beta minus, because it is for t greater than tc, it is 0. Okay, so beta plus is 0. Okay, so I just want to, so I have another nice important comment to make, and the comment is the following. I will set it in words there. So in most models, we will obtain an observable like m in our example in the Ising model. Okay, that will be called the order parameter. Okay, so what when you look at this, so you can ask, if you have a completely different problem where there's no magnetism at all, and how would you define the beta? That means you look at the corresponding order parameter and ask how does it behave where as t goes to tc. Okay, so that's how you would define. So left hand. So what I want to do you to do is to read left hand side as saying that it is the order parameter goes as 1 minus t by tc beta. Okay, is this clear?
So does this beta equal to half come when we find the root for beta less than 2? Like when we find the root,
So, so,
t
so,
less than
so the
tc.
way we solved it is that we found we near t equal to tc, we saw that we could approximate it by the cubic thing, and we found it as a root of the cube. We actually got a square root m of t goes like square root of 3 times 1 minus t by tc. That's what we got. We even got the three factors.
Okay.
Okay, so we remember we expanded tan hyperbolic as x using the tan hyperbolic of x equal to x minus x cubed by 3.
Yes.
Okay, and then it was a cubic, and we always saw that x equal to 0 was one solution, but there were two other non-trivial roots when t is less than tc.
Yeah.
Okay, so this is the order parameter, and so that's the C defines this gamma. Now, what is gamma? Okay, so gamma is the, so recall that you have chi, which is the magnetic susceptibility, and that is defined by dm by dh. Okay, you compute this, of course, at constant t, and then evaluate this at h equal to 0. This is the definition of chi of t, and so this is definition, and again this is mod t minus tc power
So isn't it dm db?
a b. Sorry, absolutely right. Thank you. Okay, so this is so this defines this new exponent gamma, and so the question is, what is gamma? So you turn on a magnetic field, and then you ask what that is. And so now let's just the way to do that is simple. So we look at that consistency equation. So in the mean field, 2m is equal to tan hyperbolic tc by t into 2m plus beta b by 2. Okay, so we just go ahead and take derivatives of this. So since we are only interested in the singularity, it doesn't matter if I put a 2 here also. Okay, we only are interested in gamma. If I put a 2 here and take derivative of 2m, okay, for it doesn't matter. Okay, so I'll just compute. Okay, tan this thing will be sec square secant hyperbolic square of the stuff times derivative of this. So it will be tc by t into d by 2m by db plus beta by 2. Right, chain rule, nothing deep. Okay, so we can simplify this. So there are two terms. We have to collect all terms which, so we take this to the left hand side. It is uh, what we get is, okay, that's what we get. So now I get a formula for where this bracket is just this whole quantity. I'll put it at the end. So 1 minus Tc by T into, okay, and then we want to set B equal to 0. Okay, so let's do that. Okay, so what do we get? So we get sec square of, after we put beta equal to 0, it is just Tc by T into 2n. Okay, and we can ask what is this when limit T tends to Tc. So we are only interested in the behavior near Tc. Okay, so here you can see that both sides go to 0. So what is sec square? What happens to sec square when 2m becomes 0? Hello, is anybody there?
Sure. So cos h goes to 1, so this also should go to
Goes
1.
to 1. That's all. Okay. So numerator becomes beta. So yeah, beta, I'll put all those things in. It will become 1 by, uh, okay. So what is gamma then? So diverges. So chi. Okay. So what is gamma now? There's a mistake in this definition of gamma. Be minus gamma. So what is gamma?
1.
Okay. So that's good. So are there any questions? So I have a puzzle or whatever which is bothering me. I want you to think about it. So uh, no, there's no puzzle. Nothing. Okay. Okay. So now we have to define the exponent delta. Which, how was delta defined? Okay, so let me just give me a second. Let me look up delta, definition of delta, fourth exponent. Yeah. So I have to explain something here. So recall that, so something said when this is computed at t equal to tc. Okay, so it's exactly at t equal to tc, but okay, where both phases coexist. Okay, what are the phases? So here the phases are f is, so here f is ferromagnetic phase and p is paramagnetic. Okay, so what happens is that at the coexistence line, that at t equal to tc, both para and ferro can coexist, but the magnetization in a para phase is 0, and in the ferro phase it's some non-trivial n when B is turned on and B is small. We are interested in when what happens when B is small. Okay, is this clear? So for instance, I'll give you another analog where delta will be defined later, and that has to do with, yeah, is in the liquid gas transition. There it will be, for instance, the difference between either the density of gas and density of liquid, or inverse of it. It could be, specific volume of liquid and difference. Okay, so that will be that's the sort of quantity that you would do. And what would be the corresponding variable? So here m and b are dual variables. Okay, remember, in my thermodynamics lecture, I talked about forces and displacements and things like that. So they pair up, right? So m goes with b. Okay, so m and b are dual variables. Okay, so b is our control parameter, and we ask how m changes, right? So that's what. Okay, so there it would be something like pressure or something, whatever. So that's what we want to work out. Okay, so this is 0, we know, and this is some non-zero, and this is equal to m. So that's how this formula is. Okay, so how do we determine delta? So now we need to determine delta. So again, we will go back to our solution. I think that's what we have to do. And hyperbolic. Okay, Tc by T. So T equal to Tc. So that will just become 2m. Okay, plus uh, beta C B by 2. Okay, so we have to now expand this tan hyperbolic. So we'll expand it. 2m plus beta C B by 2. Okay, that's the first order. Minus 1/3 whole cubed. Okay, and we want this near. Okay, so we want to expand. Okay, so first thing to observe here is that the two m's cancel out. Wouldn't be a surprise. Okay, this cancels out. And if you look here, that then if you look at the expansion of this, so what we will get is that this is equal to beta cb 2, okay, minus 1/3 2m whole cube plus lower order terms. Okay, so there will be next term which would be linear in b would be 2m whole square into beta c into b, and you have to do a little bit of thought that this term is smaller, and so we can throw these things out. Okay,
Sir, how did you get the first equation?
this one,
Yes.
this is the mean field solution. Mean field approach, this was the equation, consistency equation.
Okay.
I mean, I had this even here earlier. I don't know how many times I have written this. Even I remember now. Somewhere else I wrote. Here again. Here. Same thing. Okay, except I have Tc by T, I set T equal to 1 because T equal to Tc.
Okay.
That's all. It's the same equation as that. Okay. So now what we can see is that we get 2m whole cubed goes as b. We are only interested in this behavior for small b. Okay. Or 2m goes as b power 1/3. So what does that imply delta is? Okay. Again, you have to go back to the definition, and the definition goes like 1 by delta. Is this clear? So that's we got all the exponents, and that was the table which I showed you. Oh my god. So 1 second, sorry, in the recording it would have gone. So we need to determine delta. So I'm just repeating myself. So we look at the equation for the consistency thing, setting t equal to this thing, and we just do some manipulation. And first thing we notice is that the 2m cancels out, and then we are just left with these terms, and we neglect all these other pieces, and so we just get 2m cubed equal goes as b, or m 2m goes like b power 1/3. So delta is equal to 3. Okay, so this concludes problem 1. So problem 2 is about, this is about something called the,
So this cube root brings in the sine function also.
so you can put it as, if you want, you can put it as mod of that. I mean, so okay, so you just take the real cube root plus cube root, and that's it. Other ones will be complex, right? For cube root of unity.
No, I meant the sine function in the
Sine
question
function
is
is, yeah, that sine function is there because if b is positive, m will be positive. If b is negative, m will be negative.
okay.
Okay, so that just takes care of that. It's still there even here. It's there even here. So, okay, so when you see here itself, it is there, right? So you can see if b is negative, m is negative. Okay, so yeah, in a way you're right. I should write it as sine of b. Okay, so for the scaling hypothesis, and so what does it mean? Okay, so first thing we know, so let's do some generalities. We know that near a singular point, near a second order, let's see, second order phase transition, okay, things become singular. Okay, so in particular, if we, so in our example, so okay, so we expect, okay, so that the free energy, that the Helmholtz free energy should know that. Okay, why am I saying that? Because all the quantities which define alpha, beta, gamma, delta, they are things which you can always get by taking suitable derivatives of uh, of the free energy. Okay, so so in our example, okay, the free energy F will be a function of, I'll define something called little t, which is temperature. You will see in a moment what that is. T and the magnetic field. These are the only two control parameters in our problem, right? And so T is nothing but 1 minus T upon Tc. It's called reduced temperature. Okay, so the reason we are shifting to T is because small t is where now you are close to T equal to Tc. Similarly, small b is what we are seeing. We are interested in studying properties near T equal to 0, b equal to 0, little t, that is. Okay, so let us just do this, and so we want to study the singularity, and so first thing is we know that so we know one thing we know is that the alpha guy, so I just want to write something, so F, not with this color though. Okay, so what we can write is something like this: F of, let me use lowercase symbol for this. Okay, F of t should be writable as something like this: mod little t power alpha plus 2 times some non-singular function of, okay, Okay, so that when g of 0b is finite. Okay, and why did I put alpha here? Can someone tell me? Go back to the definition of alpha, right? What was alpha? It was an exponent of
Exponent of the
specific
specific heat.
specific heat, right? So it's a second derivative of f, okay? And we are only interested in the singular behavior. Of course, it looks very, very complicated. So it will have but one term in that thing. We'll have d square f by dt square. Okay, it'll have two derivatives and it should become like mod t power alpha, and that's what this term is doing. So this captures the exponent alpha completely. Okay, so far so good. I'm not done anything deep, right? I'm just saying the g of TB. Now is where the scaling hypothesis comes. Okay,
Sir, in the specific heat expression, isn't the exponent minus of alpha and not alpha?
yeah, then I have to put minus alpha. Thank you. Yeah, whatever was coming there. Thanks. Thanks. Okay, is this fine? Okay, so what is the scaling hypothesis? Scaling hypothesis says that the singular part of the free energy is a homogeneous function of its arguments. Okay, so we need it's a generalized homogeneous function. So I need a definition. So I will put this definition. I gave a link also to something you can see. So suppose you have some function f of some variables x1 and x2. Okay, and it's a homogeneous generalized homogeneous function. So you have to associate. So what it says is that f of say lambda power m1 x1 lambda power m2 x2 goes as is equal to lambda power some other lambda f, call it. Okay, so example is you know entropy is an extensive function. We write that, right? Okay, here m is equal to 1 for extensive variables. And what is it for intensive variables? Is m1 m2 kind of analog of that, calling it m. How do you scale intensive variables? How do they scale?
Should not
Zero.
depend, right?
Yeah, zero. That's all. Okay, so this is just an example. This is not our example, but it's fine. Okay, so what it says is that suppose so what it says here is that this guy should where so here these are like this thing t and b. So there is some scaling and f has some degree. Let's not worry about that. We will fix all those things in a moment. But so what it says here is that okay, so there is some homogeneity condition. So that will tell you that f of t and b goes as this part we saw minus alpha plus 2 times it will be g of x, where x is a scale invariant function of this thing. So it is b times t power delta. Okay, so x is supposed to be scale invariant. Okay, so what it says is that, so what would delta be? So suppose, uh, so let's say lambda power mt t should be equal to lambda power mb uh, b should be equal to lambda power mf of f of t and b. Okay, so if you want to compare with all these things, so first thing is, what is it I want to say? Yeah. So uh, so if x has to be scale invariant, so what will happen? So we will, so if you scale b, how is b scaled? Lambda power mb times b divided by t is scaled by lambda power delta into mt. This should be equal to x again. So this will require mb equal to delta mt, or delta is something mb over mt. Okay, that's what it means. So the scaling hypothesis says that this we can, and the exercise for you is what is mf. Okay, so exercise. It's not very hard. Okay, it will be some function of alpha and mt. Okay, the way I've written it. Okay, so that's what. So this is what it says. So scaling hypothesis says that things can be written in terms of scale invariant objects. So this is our thing, and b equal to 0. This better be finite. So we'll so first thing is scaling hypothesis. It's a hypothesis, just making an assumption that that has happened. So that just told you that f of uh, t and b contact mod of. We don't know what delta is because we don't know what mt is. We don't know what those are unknowns. Okay, so but we will at the end of the day we can express them in terms of all the exponents, as you will see. Okay, so this is the first assumption. Second assumption. So these are assumptions. Okay, g of x is an analytic. Okay, so that means a smooth function or derivative selections. In particular, there will be, I can do a Taylor series. So let's just do that. A0 is some constant. A1 is also some constant, which is independent of x, of course. A2, say x square. This is what it means. Okay. So we have something to go work with. So we get f of xt. Okay, so now we can, so we have other exponents which we can do, which are derivatives, right? So let's, what was beta? Beta went with magnetization. So m is df by db, right? And this goes like t minus tc, which is little t power beta, right? This is what is okay. So we have to take we have to take derivatives, and then for small enough b, set b to 0, right? After this, close to df. Is this correct? M is no.
Yes, sir. It was 1 minus t by tc, so it's proportional to small t raised to beta.
Okay. Yeah. So we have to just do this, right? So because the coupling is m dot b, we can do this. Okay. So this is what we can do. And so we just have to take derivative and then set beta equal b equal to 0 after this. So you can see here that the a0 term won't contribute. This will also not contribute because we'll put b equal to 0, x goes to 0. Okay, so df by db, with b equal to 0, we'll have one term which is 2 times a1 into uh, x, which is a1 by t power delta. Correct? So we just look at these two and we get a relationship. What is it? It says that beta equal to minus alpha plus 2 minus delta. Okay, is this fine? Just comparing, nothing deep. So this is relation 1. Second relation, we need to get gamma now. Compute. Second one is compute gamma. And what was that? C goes as t power minus gamma, right? That's what it was. So what? But what is C? C is d square f by dt square. Oh, sorry. C gives alpha. We already done that. So we have to now look at. Terribly sorry. Chi. Okay. Which, if you think about it, is dm by df. So it is d square f by db square. Okay. So now let's come back here again. Look at this. We have to take two derivatives with respect to f. Okay. So that's equal to. There will be several terms, but the dominant term. Okay. So the leading term. So we have to do. So you can see this is proportional to b. This is proportional to b square. So when you take derivatives, a0, a1, both terms won't contribute, and only this term will contribute. So this will go like t power minus alpha plus 2, and we have to differentiate this twice. A2 times b power t power 2 delta. Okay, is this fine? And so this should be equal to t power minus gamma. So that's what we have. So gamma, so what we get is minus gamma equal to minus alpha plus 2 minus 2 delta. So let's just fix things. Alpha minus 2 plus 2 delta. Okay, is this okay? I'm just matching. So I've just put in. So what I've done is two things. I assumed the scaling hypothesis. Second thing is I assumed that g of x is an analytic function. So that's a nice Taylor expansion. And okay, once I did that, I just go ahead and do compute whatever these things were, and then go back to the definitions of alpha, beta, and gamma. And you can see here that I'm not making any deep use of what my solution is. I did not have to refer to the main field solution or any solution. I just had to refer to the definition of the exponents. Okay, so we have these two things out here, and that's a nice thing that happens if you. Okay, so I want to get rid of delta, okay, because my exponents are defined. So what is happening here is you can see that it a priori it looks like alpha, beta, and gamma were independent of each other, etc. But they are related, and you can see what we can see here is alpha plus 2 gamma plus alpha plus 2 beta plus gamma. If you look at that, you will find that the delta term goes away. Delta goes away. We have a solution to that, but we'll get this. Okay, is this clear? You just have to look at these two things. So you multiply this by 2 and add. So you can see minus 2 delta and 2 delta will cancel. Okay, and then this will be 2 times this will become 4 minus 2 will become 2. Minus 2 alpha plus alpha will become minus alpha, which you bring to the other side and you get this. Okay, so implies. Okay, so the three, what we thought were three independent exponents, are actually related. And if you are able to check that this holds, then scaling hypothesis is true and the analyticity, these two assumptions at least are consistent. So now we are still left with one more, right? So what was the other one? So delta. How was delta defined? It said that m goes as b power 1 by delta or something like that, right? So we need to do this. So what is m? At t equal to tc or little t equal to 0. This is what it says. Correct? Okay, so what was m? Is df by dt dv. Sorry. And we have to evaluate this at t equal to 0, but there is some little bit of care. One has to be a little bit careful. So what was f? F went like mod t. Okay, I'm not drawing the x square term, so we can just do this. So df by dv. Okay, so so on and so forth. So you have to compute df by db, and so this will be equal to b square by, sorry, I have to take derivatives. We keep going, okay? So point here is that we have to, one thing I didn't work out, what is delta now? Delta is, there are multiple relations, but we just want something involving delta, and beta is the one which involved m, right? So let's do that. So delta is minus alpha plus 2 minus beta. Okay. So what is it I want? So I thought this should work out. So I need some help here now. So the point here is we want to ask. So there's some. What is it? The issue here is that we need to take. We need to set t equal to 0. Okay. So you need to pick out. So the So what I'm saying here is that we need, so yeah, so let's look at these terms. What is it I want? One second. I just want to see what is it I need to prove. So let's look at this. So show this. Okay, so how does that help me? So so let's look at the coefficient of a1. So a1 will be so the term involving a1. So I'm just going to write out the latest powers minus alpha plus 2 minus delta. So I won't worry about factors. So a2 will be a2 minus alpha plus 2 minus 2 delta. I think this is the stupidest way to do things, but that's okay. Okay, so this is a kind of term. So what we have to do is to, in this way of stupid way of doing it, I'll explain to you why it's stupid in a moment. We need to find out the leading non-vanishing term.
Sir,
Yeah. Yes.
I did this in one way.
Yeah.
Uh,
Tell me.
so
Yes. Yeah.
we
I
just
thought this was easy.
have
I did it in my head
to
and I didn't.
have the
Yeah.
proportionality first, right?
Yeah. Go ahead.
So it is a naught plus a1x and so on, right?
Yes.
So so can you hear me?
Yeah, I can hear you very well.
So it is x is proportional to 1 by t power delta. So if you add up the exponents
Yeah.
and if you want the scale invariance,
Mm-hmm.
then alpha plus 2 minus delta equal to 0, which will give the relation.
Alpha plus. Repeat. Alpha plus.
Alpha plus 2 minus delta equal to 0.
Uh-huh. So
If you want scale invariance.
scale invariance implies what? Alpha plus.
So it
Just
is,
say whatever we said
t
first.
power
Hmm.
alpha plus 2 minus delta equal to 0 you will obtain, because there is a delta in the denominator, like t power
Mm-hmm. Mm-hmm.
1 by t power delta, right?
Yes.
So when it comes up, it will be minus delta.
Yeah.
So that multiplied by t power alpha plus 2 outside, which is already there.
Mm-hmm.
If you want this power exponent to become 0, which basically means scale invariance, then you get the relation.
But it's not. I mean, but that's not supposed to be scale invariant, right? It cannot come from the
Oh,
A1 terms, right? I mean, that's what I'm saying. It cannot come from the A1 term, right? So let's just let's look at this term, right? That's minus alpha plus 2 minus delta. To come back and see, that should be some beta or something, right? Is that beta? Okay, right? Isn't that correct? That's beta, no? Minus alpha plus 2 minus delta is beta. I think it will come to what you're saying, but just okay. So what?
Okay.
Okay, so we will use scale invariance, but now I mean, so what I'm saying here is nothing wrong with all these things, but there's a simpler story here, I think, which is to do the expansion. So f of t and b, I wrote it as this thing, but I could write it in a slightly different way. I can write it as b power. Okay. So what was the definition of beta? Okay. Uh, so what I want to say, f of, so my idea here is to pull out. So if I want beta for chi, one second, gamma. What was the expression I wanted? Gamma, right? And delta should come in here. Ah, okay, good, good. So, so chi, which was just dm by db, dm by db, right? Is that what it is? Which would be second derivative, right? Okay, so and this should go like uh, t little t power minus gamma. This is what we have, correct? This is what we get, and so what I want to do here is to write this in a slightly different form. I wanted to give a different expansion where I write pull out. Yeah, yeah. So let's. I'm also getting confused now. Okay. So if you're looking at df square by dc square, we'll get it from here, this term, right? So it will come from here. So, but that is already something we already used, and we got gamma equal to alpha minus 2. So yeah. So we're getting those. So this is beta and this is gamma, is it? Up to some signs. That's what it says. Okay, I give up. I am confused about this proof, so I should have worked it out. I didn't work it out. I thought I can do it, and it's not happening. So exercise, or I'll write it. Okay, exercise to the other to the relation. Okay, so but it should come. It should come from a singular argument. Okay, what I'm trying to say here is the reason I'm going to these various orders is that it should come for me. So this goes like b. Okay, a1 is independent of b, a2 as a b, this has a b square, and this has a b cube. Okay, so what I'm trying to say here is that it should happen that this particular term, okay, should give the correct whatever, scaling or whatever, and because it should give b cubed. Oh no, wait a second. So what is it I'm saying? What I'm saying, we should look for the first non-trivial guy. Yeah. So yes, so we should look for the guy which, when I take t equal to 0, remains, okay, the dominant term. All the other terms will be further and further smaller. And okay, so that's what we want. So we want the leading term. I'm not able to see it. Okay. So I think I'll stop here, and I'm really sorry, but that's the way it is. I'm not perfect.